Good evening, this is Jayagrishan. Welcome to the session of Engineering Mechanics. In the previous classes, we have been discussed about the concept of center of gravity, first moment of area with respect to x and y axis, and how to calculate the center of gravity of a plane lamina using first moment of area principle. Previous session mainly focused on a single lamina of known shapes or a composite lamina which can be subdivided into known shapes for determining its center of gravity. Today, we will see how to determine center of gravity of plane figure which may not be easily divided into known shapes. However, it can be divided by area under or area between two lines which can be expressed as functions. The key concept behind the calculations involved here also is same as that of first moment of area principle. To explain the method of center of gravity determination using direct integration method, we consider a right angle triangle as shown in the left side of the slide. Now you may have a question. Initially I told that the method is useful for the shapes which may not be easily converted into regular shapes or which may not be a regular shape or non-shape. Now I am considering a non-triangular shape. Let me clarify it. Basically, the method can be used for any shape which can be expressed as a form of area formed by a function or area below a function. Further, for the easiness of understanding, I am considering a rectangle triangular section. Okay, come to the point. On the given figure ABC, the vertices of triangle is also mentioned here. And we can say that area under line AB, which is displayed in the right hand side of the presentation or slide, that is the line AB which starts from the point 0, 0 and ends at AB, that is passing through point A and ends at point B, or starts from point A and ends at B, can form the right angle triangle considered in the left side image. And we all know that the line AB can be expressed as a function of y is equal to mx plus c, or we can say the equation of line AB will be is equal to y is equal to mx plus c, where m is the slope of line and c is the intercept in the y-axis. And for better understanding, here we can see on the figure 2 that the area, how the area forms a triangle. The next step involved in the direct integration method is to identify or calculate the constants in the equation. For that, we can use the boundary condition, the given boundary conditions of the plane lamina. Since the line AB passing through origin, we can say that the value of y-intercept is 0, that is c is equal to 0. Or else we can calculate the value of y-intercept by applying boundary condition at origin, that is 0, 0. And similarly, to find the value of slope, that is m, I am applying the boundary conditions of b, that is, we can rewrite the equation as b is equal to ma. And from that I am writing down that m is equal to b by a. Now we have the values of m, which is equal to b by a, and the value of c is equal to 0. And now let me rewrite the equation of line y is equal to mx plus c as y is equal to b by a x, and denoting it as equation 1. And moving to the next step. The next important step in determination of center of gravity by integration method is selection of a small, extremely thin rectangular strip which is passing through the functional line. and it is shown in the figure 3. And from figure 3 we can see that there is a small strip of thickness dx is marked there at a distance x from y-axis, which is passing through the functional line at point with the coordinates x comma y. And the basic key idea of this method is calculation of area and first moment of area with respect to the axis of this particular small selected rectangular strip, and integrating the area and first moment over the boundary condition will give you the total area of the lamina. Similarly, the integration of the first moment of area of the small selected rectangular strip will give you the first moment of area of the lamina. And once we have first moment of area and total area of the plane figure, we can calculate the coordinate of center of gravity by using the formulas discussed in the previous session. That is, x bar is equal to qy by a and y bar is equal to qx by a. Now we select a small rectangle of thickness dx at a distance x from y-axis. And to proceed further, we have to identify its area and coordinates of center of gravity. The center of gravity of selected strip can be written as x bar, small x bar is equal to x plus dx by 2, and small y bar is the y coordinate and it is equal to y by 2. However, the thickness is assumed as extremely thin, and we can consider it as a negligible one compared to the x value. So I am rewriting the center of gravity coordinate of the small strip as x comma y by 2. Okay. Now move to the area part. The small rectangular strip's area I am denoting as dA, and it can be calculated as dx into y. Yes, dx into y. And for the purpose of integration, as I said earlier, for the purpose of integration of the upcoming steps, I am substituting y is equal to b by a into x in equation 2. That is, equation 2 is denoted by dA is equal to dx into y, where in this equation I am substituting y as b by a into x. Now the equation 2 will be rewritten as, can be rewritten as dA is equal to b by a into x dx. And the next step, I am calculating the first moment of area or small strip with respect to y-axis. I am denoting it as dqy, which is equal to x bar of element into dA, that is small x bar into dA. And similarly, I am denoting the first moment of area of small strip with respect to x-axis as dqx, which is equal to y bar of element into dA. And now I am moving to the calculation of total area of triangular lamina. The total area of triangular lamina can be calculated by integrating the small area, strip's area dA. That is, total area of lamina can be denoted as capital A, and capital A is equal to integral small dA over the limits 0 to a. And dA can be written as b by a into x dx, and I am integrating. Upon integration and applying limit, I will get the value as ab by 2. Then the first moment of triangular lamina can be obtained by integrating the first moment of area of the small strip with respect to the respective axis. So in order to get the first moment of area of triangular lamina with respect to y-axis, that can be noted as qy, capital Qy, which is equal to integral of x bar element into dA over the limits 0 to a. And upon solving the equation, integrating and applying limit, I will get the value. I am getting value of qy as b square by 3. Similarly, qx also can be calculated as b square a by 6. Now we have the total area AB by 2 and forms first moment of the triangular lamina with respect to y-axis as BA square by 3 and first moment of area of triangular lamina with respect to x-axis is b square a by 6. Now we can calculate the centroid coordinates of center of gravity or centroid of the plane figure capital X bar and capital Y bar as capital X bar is equal to qy by a, which is equal to 2a by 3, and capital Y bar is equal to qx by a. Upon solving substituting and solving the values, I will get the value of Y bar as b by 3. By this, let me summarize the steps involved in the determination of center of gravity using integration method, direct integration method is. The first step is to identify the function of line. Secondly, we have to determine the values of constant in the functions. And third step is selecting a small rectangular strip touching the functional line or functional lines. On to the next, we have to determine the center of gravity, the coordinates of center of gravity and area of the small strip selected. The next step, that's the fifth step, is integrate the area of strip to get the complete area of given 2D lamina. As a sixth step, we have to calculate the first moment of rectangular strip, selected rectangular strip, and integrate for the first moment of given 2D figure. And the final step is to calculate coordinates of center of gravity from the obtained first moment of area and the total area. One more thing need to be kept in your mind is we can select both either horizontal, not both, either horizontal or vertical rectangular strip. If it is a vertical strip, we have to integrate over the maximum x value from 0, and if it is a horizontal strip, we have to integrate from 0 to maximum y value. However, the strip is either vertical or horizontal, it should be touching the functional line, even though it may be a vertical or horizontal. It should be passing, or one point should be lying on the functional line selected. And I hope that you got some insight about this determination of center of gravity using direct integration method. And here there is some examples and solutions, along with the one practice problem is attached. Try to solve it and get back. Thank you.